Hello guys, welcome to another video. Today we're going to work on topic 12 for HL. We're going to solve a couple of problems. So without further ado, let's jump straight to the paper and see the solution. So the first question, it is about a diagram that it shows the end of an electron diffraction tube. A pattern forms when diffracted electrons are incident on a fluorescent layer at the end of the tube. And the first question it asks, explain how the pattern demonstrates that electrons have wave properties. And you see 3 marks. So there are 3 points that we need to make. Now, first of all, what do you see? Here in the tube, we see that there are bright and dark fringes. So we observe bright and dark fringes. But this, it comes from constructive and destructive interference, as we have seen already in the previous topic. But interference, it's a characteristic of a wave. So this is how we explain the electrons that they have the wave properties. These 3 points you need to make and you get the full marks. The next one, 6C. Electrons are accelerated to a speed of 3.6 times 10 to the power of 7 meters per second by the electric field. Number 1, calculate the de Broglie wavelength of the electrons. For number 1, we know that the Broglie wavelength is given by this formula, H Planck's constant over P, the momentum of the electron. Now the momentum of the electron, it is the mass of the electron, you can find it in your data booklet, times the speed of the electron. So having these numbers, if you do your calculations here, you're going to find a value of 3.28 times 10 to the power of negative 23 kilograms times meters per second. So having that, we can apply this in your formula. Of course, H, Planck's constant, it's 6.63 times 10 to the power of negative 34. These are just the numbers that we use. So 3.28 times 10 to the power of negative 23. You do the math here, and what do you find? You find a value of 2.02 times 10 to the power of negative 11 meters. And number 2, the cathode and anode are 22 millimeters apart and the field is uniform. The potential difference between the cathode and the anode is 3.7 kilovolts, so that the acceleration of the electrons is approximately 3 times 10 to the power of 16 meters per second squared. So now what do we do here? There are 2 ways. I'm going to show you the long way and I'm going to show you the short way as well. Now you see here 5 marks. The first exercise, it was 2 marks. One is to calculate the momentum and the other one was to calculate the wavelength. Now for this one now, what we can do? We have the potential difference between the anode and the cathode, and we have also the distance apart. So with this one you can calculate the electric field, that is V over D. So if you do the math here, you find 1.68 times 10 to the power of 5 volts per meters. Now having this, you can find the force that is exerted on the electron. The force, it is the electric field times the charge of the electron. The charge of the electron can be found in your data booklet. If you do the math here, you find 2.69 times 10 to the power of negative 14 newtons. And now, of course, you can apply Newton's law. So for acceleration, force divided by mass, you have the mass of the electron. You do the math here and you find a value of 2.9 times 10 to the power of 16 meters per second squared. And these are your 3 points that they remain from the exercise. Now there is another way also. The other way is a little bit easier. The other way is to find the correct kinematic equation. Now here you see that we don't have time, so we use the third one, and this is your first point. Your second point is to rearrange this one, solving for A. Of course, initial velocity is 0. So you have V squared over 2 times S, and here you apply the numbers that you have. You have 3.6 times 10 to the power of 7 divided by 2 times, the distance is 22 times 10 to the power of negative 3 meters. And your third point, of course, is to give the correct answer. But if you do the math here, it's going to be the exact same value, 2.9 times 10 to the power of 16 meters per second squared. Now it doesn't matter which way you choose, both of them are correct and acceptable, so choose whichever one you feel more comfortable. 6D. State what can be deduced about an electron from the amplitude of its associated wave function. Now here, what do we talk about? Of course, we talk about this formula. So what do we say here? We say that the probability to find an electron at a specific point is proportional with the amplitude of the wave function squared. So probability to find an electron at a specific point is proportional with the amplitude square of the wave function c. 6e. An electron reaching the central bright spot on the fluorescent screen has a small uncertainty in its position. A small uncertainty in position. Outline what the Heisenberg uncertainty principle is able to predict about another property of this spectrum. Now, what Heisenberg uncertainty principle says that the product of the uncertainty in position and momentum is constant. So, actually this relates the position with momentum. And this is your first comment for your first mark. And what does that mean? It means, for your second mark, the more we know about the one, the less we know about the other. So the more we know about the position, small uncertainty, so we have a lot of details about position, then the less we know about momentum. The next question is about nuclear energy and radioactivity. The graph shows the variation of binding energy per nucleon with nucleon number. The position for uranium-235 is shown. So here you can see the position. The uranium-235 can undergo alpha decay to form an isotope of thorium. Number one, it asks state the nuclear equation for this decay. And this is something very simple for us. We already know 235, 92 uranium. It will go under alpha decay, it will create an isotope of thorium. Now, alpha decay, of course, it is an alpha particle or a helium particle. So it has 4 nucleons, so it's going to be 203, 1. And of course, 2 of them, they are protons, so it's going to be 90 here. Plus, of course, the emitted particle, it is the alpha particle. Even if you won't write helium here, is acceptable. And this is the equation for the decay. The number 2, it says, a sample of rock contains a mass of 5.6 milligrams of uranium-235 at the present day. The half-life of uranium-235 is 7 times 10 to the power of 8 years. Determine the initial mass of the uranium if the rock sample was formed 3.9 times 10 to the power of 9 years ago. So what do we do here? Of course, when we have to deal with this situation, we need to use the decay formula. And the first thing that we have to do is to determine the decay constant. So an activity of a sample, it is A0 e to the power of minus lambda times t. And I want to solve for lambda here. Now for half-life, my activity, it will be A0 half, it is equal with A0 e to the power of negative lambda, and the half-life in this situation, it is 7 times 10 to the power of 8 years. So I'm going to use this value here. Of course, these, they cancel out. I need to take ln from both sides, so you have ln 1 over 2 is equal with ln e minus lambda 7 times 10 to the power of 8. Now from here, you need to do the calculations. ln 1 over 2, it's minus 0.69, and this is equal with minus lambda times 7 times 10 to the power of 8. So pretty easy from here, you just solve for lambda, and you find a value of 9.9 times 10 to the power of negative 10, 1 over years. This is the unit for the decay constant. Now, since you have the decay constant, you can apply the formula in your specific problem. And of course, the activity that you have now, actually the mass in this case, it is equal with the initial mass times e to the power of negative lambda times t. So what are you looking for? You're looking for the initial mass. So you need to solve this formula for m0, that it is m times e to the power of lambda times t. And from here, you need to use, of course, the correct time. Now, when was this formed? This time ago. And of course, your mass is the mass that you have right now. So what do you have now? 5.6 e to the power of 9.9 times 10 to the power of negative 10 times the time, 3.9 times 10 to the power of 9. And you do this simple calculation here. So you see that the initial mass, it is 266 milligrams. Okay, be careful with the units. Here we have milligrams. I didn't change anything here. Here we have years and 1 over years. They cancel out, don't worry about it. The next question is about the photoelectric effect. In a photoelectric experiment, light of wavelength 450 nanometers is incident on a sodium surface. The work function for sodium is 2.4 eV. Calculate in eV the maximum kinetic energy of the emitted electrons. So number one, super simple. We just need to apply the formula. E max, you can find in your data booklet. It is H times F minus phi, the work function. So what do you have here? Here you see frequency. You don't have here frequency, you have wavelength, but this is not a problem. It is H times C over lambda minus phi. Now this is a constant. It is given in your data booklet in eV also. So you don't have to worry about calculating Planck's constant and speed of light and then convert this into eV and so on. So you can have this specific value. It is 1.24 times 10 to the power of negative 6 eV times meters divided by 450 times 10 to the power of negative 9 meters minus the work function is 2.4 eV. So the meters, of course, they cancel out. You do the math here, eV in both terms. So pretty easy. You just find a value of 2.76 minus 2.4, and this is equal with 0.36 eV. And the number two, it says the number of electrons leaving the sodium surface per second is 2 times 10 to the power of 15. Calculate the current leaving the sodium surface. This is even simpler. You just have to think about that the current, it is the charge that it flows under a specific amount of time. Now, how much is the charge? You have the number of electrons. So the charge, it will be all the electrons multiplied by the charge of one electron divided by the time. The charge of one electron, of course, you know how much it is. So what do you have here? The number of electrons over the time, this term, is given. So you have 2 times 10 to the power of 15, because it says per second. Read carefully. What do you have here? Times 1.6 times 10 to the power of negative 19, and this will give you a value of 3.2 times 10 to the power of negative 4 amperes. Now the next one, it says that the wavelength of the light incident on the sodium surface is decreased without changing its intensity. Explain why the number of electrons emitted from the sodium will decrease. You see 4 marks, so we need to make 4 points here. Now, we have seen this before, especially in the multiple choice question. It's very usually that you are going to meet a problem like that. So what it says here, the wavelength is decreasing. So that means that the frequency, it will increase. And that means that the energy also is going to increase as well. Now, what do we have? We have the same intensity, but with more energetic photons. So that means that we need less photons. So we have less photons, so fewer photons interact with electrons, so fewer electrons too. And these are your 4 points that you need to make to get the full marks. The number 23A, it says, the one, define the term unified atomic mass unit. This is something that we know from your book. It's one definition that you should not forget. So it's the 1/12 of the mass of a carbon-12 atom. Remember, I have said that we cannot lose points because of definitions. I have gave you in the resources also a paper with all the definitions that you need. So be sure that you memorize that and you understand. Number 2, it says the mass of a nucleus of Einsteinium 255 is 255.09 U, the unified atomic mass unit. Calculate the mass in MeV over C squared. Okay, so what do you do here? Here you know that one unified atomic mass unit is equal with 931.5 MeV over C squared. So what you need to do is to just replace that. So 255.09 times 931.5 MeV over C squared, and this will give you a value 237,600 MeV over C squared. So 23B, it says when particle X collides with a stationary nucleus of calcium-40, a nucleus of potassium and a proton are produced. The following data are available, the rest mass of each particle. The number 1, it says identify particle X. Of course, we can take a look at the atomic mass and the proton number of the particles here. And what do you see? You see 40 and 20 initially, and then you have 40, 19 and 1 proton. So it's pretty clear here that the proton number was reduced by 1, but the nucleon number, it stayed the same. So of course, what this can be, it can be 1, 0, and this is a neutron. So the particle X, it's a neutron. Number 2, suggest why this interaction can only occur if the initial kinetic energy of particle X is greater than a minimum value. We know that the mass of the products here, the mass of the products, the combined mass, is bigger than the mass of the reactants. This energy, the extra energy, needs to supply it in the system in order to create this mass. The mass of the products is bigger than the mass of the reactants, and so energy must be given to supply this extra mass. And these are the 2 points here, because this it has 2 marks. The first one, of course, it was 1 mark, and the remaining 3 marks are for the last one. And now let's see also the last one, number 3. It says, before the reaction occurs, particle X has kinetic energy of 8.326 mega eV. Determine the total combined energy of the potassium nucleus and the proton. What we need to do is to calculate the energy needed, the required energy for this reaction, and then we see the difference between the initial kinetic energy and of course the energy that the reactants have. Mass defect. We need to see the difference in masses. So the mass defect, it will be equal with a combined mass of the reactants, so potassium and proton, so the mass of potassium plus the mass of the proton, minus the mass of the reactants. Sorry, before I think I said reactants is the mass of the products minus the mass of the reactant. So you have the mass of the calcium plus the mass of the neutron. Now you have every number here. I'm not going to do the substitutions. I'm just going to give you the difference in mass in the end. Just practice it by yourself. It's going to be 0.573 MeV over C squared. Now when you have the mass defect, you need to find the energy required for this reaction. And what is it? Of course, from the famous equation mc squared. So here you see the units of the rest mass, so you don't have to do anything here. 0.753 C squared times MeV over C squared. These cancel out. So you have MeV. And now, the rest energy of neutron that it had initially, it will be given to the kinetic energy of the product. So the total combined energy of the products, what will be? It will be the initial kinetic energy of the neutron minus the energy required for this reaction. So 573, and if you do the calculations here, you have 7.753 MeV. And these are your 3 points for this mark. So that was all for today, guys. Topic 12, it can be a scary topic. It's not difficult. It is just that sometimes it can be obscure. But anyway, you need to study hard, and good luck.